everyone and welcome. Let's talk about the sun. So the sun is the source of basically all power in life on Earth, so it's pretty important. But where does the sun get that power from? So you may have heard the sun described as a giant fusion reactor, or maybe even a fusion bomb. I've described it similarly. And so yes, it's fusion. Fusion is what's powering the sun. But I think we can do a little bit better than that. So by mass, the sun is composed primarily of hydrogen. It's about 70.6% hydrogen, and then about 27.4% helium. And then the remaining 2% are just other metals. So fun fact, anything that's not hydrogen or helium, astronomers call metals. So even things like oxygen, they call metal. So why is this important? So hydrogen and helium, if you look at this curve, which is called the binding energy per nucleon curve, you can see that the jump between hydrogen and helium is pretty large, and it's in a positive direction. So the way to read this curve basically is as you move from hydrogen to helium, your binding energy per nucleon is increasing, and so if you fuse hydrogen into helium, you are releasing energy. And actually, if you'll notice something interesting about this curve, right, it increases up to a peak and then it starts to decrease again. And so this means that everything up to this peak will give you energy when you fuse them together. And this peak occurs at iron. And so this is why basically stars can produce all the elements up to iron. But if you go past iron, the curve starts to decrease again. So as the direction of this curve changes, then that means that now if you fuse them together, it takes energy, but if you break them apart, it gives you energy. And so that's how fission works. But you can also see that the slope of this curve is a lot less, and so that means fission is basically giving a lot less power than fusion. And so going from hydrogen to helium is basically this enormous leap, and it produces a ton of energy. Okay, so when we're talking about these elements in the sun, we're pretty much talking about the nuclei of the elements, right? It's very hot, all of these elements have been ionized, that is, their electrons are not attached to them anymore. So if we're just looking at the nucleus of a hydrogen atom is just one proton. So when we actually talk about the sun being composed of hydrogen, we actually really mean it's just composed of protons, just single protons. So if you'll think back to your high school chemistry class, right, helium has the atomic number 2, which means that it must have 2 protons. So a typical helium nucleus is 2 protons and 2 neutrons. And this is also called an alpha particle. Okay, so you have hydrogen with its 1 proton, and you have helium with its 2 protons and 2 neutrons. Now if you added up the mass of 4 hydrogens, and you had the mass of an alpha particle, you would notice that those masses are not exactly the same. They're very slightly different. And that difference is where the energy comes from. Now this goes back to one of the most famous equations in the world, which is E equals mc squared. So energy and mass can be converted between one another, and in this case, you're converting that little bit of mass change into energy, and that's the energy that is produced by fusion. So basically, you're starting with 4 protons and you're ending with 2 protons, 2 neutrons in the helium nucleus. And then you also have to have 2 positrons to keep the charge the same. And you also produce 2 neutrinos and 2 photons. And those neutrinos and photons are basically what we talk about when we talk about the energy being produced. They're the things that have that energy. And so this process of fusing hydrogen together into helium is actually what defines a star as being a star. You have to be able to burn hydrogen and fuse it into helium in your core in order to be a star. If you don't have enough mass to reach the right properties in the core, then you will just be a brown dwarf, or even a planet if you're small enough. And so this is a very important process. That's really just at the core, well, literally at the core of the star, but figuratively at the core of life on Earth. So how exactly does this work? How do you start with 4 protons and end up with all of these other things I just said? Well, okay, so you could just have 4 protons run into each other at the exact same time and produce those, but that's not really very likely. I mean, it would have to be literally the exact same time, 4 different particles. That's just so vanishingly unlikely that it's pretty much never going to happen. So instead, you actually need a chain of reactions that can start with these 4 different protons, end up with these helium, and the other items released. But there's kind of a series of intermediate steps, and all of these steps are more likely than a 4-body collision because they usually involve just 2 particles. And so we call this the PP chain, or proton-proton chain, and this is the majority of what's happening in the core of the sun. In fact, it's about 99% of the fusion that's happening in the core of the sun is the PP chain, so this is very important. And there's actually 3 different ways that you can start from the hydrogen and reach the helium, and so we call these PP1, PP2, and PP3. Now, there are different likelihoods associated with these because there's certain reactions that are more or less likely to happen. And so that's in kind of decreasing order of likelihood. So PP1 is the most common, PP3 is very rare. So pp1, like I said, is very common. So about 69% of the pp chain that's happening in the sun is pp1. So the process here is you start with two hydrogens that interact with each other to create a deuterium. So a deuterium is a type of hydrogen. So it has one proton, right? Because it's still hydrogen. But it's basically heavy hydrogen because it also has a neutron. So changing the amount of neutrons in the nucleus of an atom doesn't change what type of element it is, it just changes the mass. So then you have one of these deuteriums floating around and it meets another hydrogen, and together the deuterium and the hydrogen make a helium-3. So helium-3 is helium, so it has two protons, but it only has one neutron, so it's a lighter version of the typical helium, which has two neutrons. So then if two of these helium-3s meet each other, they can interact to produce one helium and two hydrogens. So basically the two protons go off on their own as new hydrogen nuclei, and you end up with one nucleus with the two protons and the two neutrons. And at various stages of this process, the neutrinos and positron and photons are released. So the pp2 chain is relatively common. So 69% of the time you do pp1, 31% of the time you do pp2. So it starts out the same way. You have the two hydrogens making a deuterium, and the deuterium and another hydrogen making a helium-3. But then it proceeds slightly differently. Instead of that helium-3 interacting with another helium-3, instead it finds a helium-4, or a stereotypical helium nucleus to interact with. And so then that makes an element called beryllium-7. And if beryllium-7 captures an electron, then it can become lithium-7. And then if that lithium-7 meets a hydrogen, then they can become two helium nuclei. And again, at various steps in this process, the positrons and the neutrinos and the photons are released. I'm not really getting into the exact details here. And so then there's good old pp3. So pp3 is a sub-branch basically of pp2, and it only happens for 0.3% of things that start going down the pp2 branch. So this is a very rare process. And basically, it starts out the same as pp1 and pp2, and then it's similar to pp2, that it forms the beryllium-7. But now, instead of interacting with an electron, the beryllium-7 interacts with another hydrogen and produces boron-8. This boron-8 is not stable and it decays into beryllium-8, and then beryllium-8 is not stable either, and so then that decays into two alpha particles, or two helium-4s. So that's the pp chain. That's how you take this whole mess of protons and they can interact with each other and create heliums, and along the way they create these positrons, neutrinos, and photons. But I said that the pp chain was only 99% of the fusion, so what's happening with that other 1%? Well, that's the CNO cycle. CNO is carbon, nitrogen, and oxygen. Now, carbon, nitrogen, and oxygen are used in the CNO cycle, and that's how it gets its name, but they're just catalysts for the process. So they're both used and produced by the cycle, and so you just need some CNO in order for the cycle to happen, but it's not burning up the CNO in the same way that, say, the hydrogen is actually changing into helium. The CNO is just there being used by the other particles. So the cycle works like this. You have a carbon-12 that interacts with the hydrogen, and that makes a nitrogen-13. That nitrogen-13 decays into carbon-13. That carbon-13 finds another hydrogen to make nitrogen-14. That nitrogen-14 finds a hydrogen to make oxygen-15. That oxygen-15 decays to nitrogen-15. Then that nitrogen-15 finds another hydrogen and makes carbon-12 and a helium particle. So you can see that you started with carbon-12 and a hydrogen, and you end with carbon-12 and a helium. And just like with the pp chain, you're releasing positrons, neutrinos, photons along the way. I haven't gone into the exact details of any of these reactions. There's also a different way that the CNO cycle works, but that is literally only 0.04% of the CNO cycle, which is already only 1% of the sun, so I didn't think it was worth getting into. So this is the main process for the CNO cycle. So if this crazy pp chain CNO cycle stuff is enough to power the sun, which is a lot, why do we not just have fusion happening all the time? Why haven't we made fusion reactors here on Earth? Well, because this is really actually very difficult to do. So remember I said it's not really likely that 4 protons are going to interact at the exact same time to just spontaneously create a helium. Well, none of these other things are very common either. They're just more common that they actually can happen, but you still need to have a really large amount of interactions in order to get these to happen. So in order to have enough particles in a close enough proximity that they're actually colliding all the time and having this happen with any sort of likelihood, you need very, very dense material. Also, we're talking primarily about protons and neutrons, right? So these are all positively charged particles. So if you think about back to maybe, I don't know, chemistry or something, and you think, oh, okay, positively charged things, they repel each other, right? So positive attracts negative, but positive and positive are going to repel each other. And so you actually need to overcome that force. So that force that's repelling the positively charged particles is a Coulomb force, so it's basically electromagnetism, right? But if you can get the particles close enough together, then electromagnetism is not the dominant force. Then you start getting into nuclear forces. And this is how, a nucleus can be held together even though it's composed of protons and neutrons. You need these objects to get close enough, and they have to overcome what's called this Coulomb barrier. So basically they have to get close enough for the nuclear forces to take over from the electromagnetism. And so for that to happen, they have to have really high energy so that they kind of are racing past this Coulomb barrier. And so for that, you need very high temperatures, because the temperature is related to how fast particles are moving. So with higher temperatures, they're moving faster and they can overcome this Coulomb barrier. And like I said, it also needs to be very dense, so these interactions are actually happening all the time. So you need very hot, very dense material, and that is why the core of the sun is the only place that this is happening in the sun. This isn't happening in the outer layers of the sun, not in the main sequence, because it's just not dense enough and hot enough. And this is why it's very difficult to create a fusion reactor here on Earth, because we have to create these sort of very dense, very high temperatures and control them, which is very difficult to do. And I keep mentioning these neutrinos and photons and positrons that are being produced at various stages in these cycles and chains. So that's where the energy is actually carried away from the sun, in the neutrinos and in the photons. Now neutrinos are very, very tiny particles, so they have almost but not quite zero mass, and they almost never interact with matter. They basically leave the core of the sun where they're produced by these processes. They pass straight through the sun, they pass straight through the earth, they're passing through you at this very moment. They don't care. They really don't like to interact with matter, and so they just kind of go off and do their own thing. So they're not really what's responsible for bringing the sun's energy to us, because they don't interact with the earth. They don't really care about the earth. Photons, on the other hand, photons are amazing. Photons are what we see when we see sunlight. Photons are what bring the energy of the sun to the earth, because photons interact very strongly with matter. But because photons interact very strongly with matter, they don't just leave the core of the sun and come straight to us like neutrinos do. So once a photon leaves the core, its journey through the rest of the sun actually can take millions of years, because the sun's material is so dense that the photons are basically just bouncing off the particles constantly. And so they're not necessarily traveling straight outward, they're bouncing in random directions, and they only manage to escape when they happen to bounce enough times in the outward direction rather than any other direction. So it's kind of what's called a random walk through the sun. So once the photons actually reach the outer layer of the sun, then they are free to travel kind of directly out. And at that point, it takes about 8 minutes to reach us, based on the distance from the sun to the earth. But to reach us from the core of the sun, the light takes millions of years, which I think is really interesting. Okay, well, hopefully you learned a little bit of something about how the sun works and how it gets its power that is responsible for us having pretty much everything we have here on Earth. Pretty amazing that just some protons banging around together really can do that, but that's science for you. Well, thanks so much for watching. I hope I'll see you again soon. Bye.